polynomial functions of higher degrees. I think you saw or you did some of this in Algebra 2, but we'll teach it from scratch just in case, in the off chance that you forgot something that you learned last year. Let's start with one that we know. In fact, one that we were working with just now. ax squared plus bx plus c. What's that called? A quadratic. And we would say that is a second degree polynomial function. Lots of words there. Second degree because the highest power is 2. Second degree. Well, let's go up one. ax cubed plus bx squared plus cx plus d. Do you know the fancy name for that one? A cubic. That would be a cubic equation. And even easier, that would be a third degree polynomial function. And you could keep going. We're going to write one more example, but we don't need to write 4, 5, 6, 7, 8. Like they follow the same pattern. So it's like dot dot dot. F of x equals ax to the 7th plus bx to the 6th. Plus you get the idea. We don't need to write all those terms out. I don't know what the 7th special name would be. Right? 4 would be quartic, 5 would be quintic, 6, 7, 8. 8 might be like octic, but it doesn't matter past 3 or so. But we could say that it's a 7th degree polynomial function because the highest power was 7. So that's the kind of things we're looking at today. So things are going to get far more complicated. Yesterday there was ax squared. We had 2 answers. There was a bunch of different ways to solve it. Today we're going way up there with some crazy high degrees. But even still, there's a lot of things those polynomials have in common and ways we can look at them. So we'll talk about some characteristics of them. First characteristic, we've already used this word, their degree. Is the highest power of x. And it tells you the maximum number of zeros, roots, x-intercepts, solutions, like all those words that we use interchangeably. The degree tells you how many solutions there are. So we didn't talk about this much yesterday, or maybe not at all, but the quadratics all had 2 answers. Sometimes there's like a double answer. That's why we get this maximum from. Sometimes we double count things. But a quadratic will never have more than 2. A cubic will never have more than 3, and so on. And you can kind of use that in reverse. So if you draw something like that, slowly, carefully, so you get the same number of zeros I've got. 1, 2, 3, 4, 5. 5 zeros means this is at least a 5th degree polynomial. I think you can think that through because each of those zeros would have come from a factor. So that one might be x plus 1, x minus 1, x minus 3, x minus 5, x minus 8, whatever. 5 factors. If you multiply them all out, I don't know what you'd get, but I do know you'd get an x to the 5th, and then a whole bunch of other stuff. So degree and number of solutions goes together. Cole.
So like for all these graphs on worksheet 4 where it says match each graph with its function and just count the number of solutions.
So you're peeking ahead, which is fine. There's more to it than that. There's more to it than that because some of these, like you look at your answer choices, there's multiple ones with x to the 4th, there's multiple ones with x to the 5th, multiple ones with x cubed, and multiple ones with x squared. So yes, that gets you started on narrowing it down, but there's more to it, and the more to it is their end behavior. If the lead coefficient is, so there's two things the lead coefficient could be. It could be positive or negative. To me, this one makes sense. If the lead coefficient is positive, then the right end is up. If it's negative, the right end is down. So maybe it's as simple as a parabola. Maybe it's as crazy as, who knows. But if the right end is, if the lead coefficient is positive, the right end is going to be going up. And again, who knows how crazy it is. But if the lead coefficient is negative, then it's going down on the right end. So right end up. So the lead coefficient tells you what the right end is doing. If the degree, this one's a little bit trickier because all our degrees are going to be positive, so it's not a positive negative thing. If the degree is, it's even versus odd. The degree is even. What do you, any thoughts if the degree is even? What's the left end doing? Think about a parabola. That's the easiest one to think about. So it's not necessarily going down, it's not necessarily going up. Joseph?
It's going the same way as the other one.
It's going the same as the right end. So if the degree is even, the left end is the same as the right end. So the degree by itself doesn't really tell you which way the left end is going. It only tells you what it's doing relative to the right end. So again, if you get stuck on these, you think about a parabola, because you're pretty good with parabolas, you can picture those. If the degree is odd, then the left end is opposite the right end. And you think about a cubic. A cubic going the opposite of the right end. If it helps, odd and opposite both start with O, so those kind of go together. So the right end we get from the lead coefficient, the left end we sort of get from the degree, but only after we know what the right end is doing also.
So I might be jumping ahead, but like for number 6 in the second section, it looks like it has 2 roots. Different. So it would be a negative and an odd.
Yes, so this would mean the lead coefficient is negative. The fact that they're different means the degree is odd.
So it can't be 2.
Now it does look like it has 2 roots,
So we would have
but do you remember, like you are jumping ahead a little bit, when it bounces, there's a special name for that kind of root? It's called a double root. So it kind of counts twice. And so there are 3 zeros there, and so that makes it match up with being a third degree with the lead coefficient that's negative. Let's look at some pictures. Let me make a little table here. So 4 very simple graphs, meaning, well, they're simple, I guess, but they don't have to be exact, right? I don't even have an X and Y axis on there. So just get the shape right. And then we'll make a table to talk about their lead coefficient and their degree. So this is what Cole was looking at a minute ago. So lead coefficient on this first one, is the lead coefficient positive or negative? Positive. How about on the second one, lead coefficient positive or negative? How about the third one, lead coefficient negative, and the last one negative. Degree, we're not talking positive, negative, we're talking even, odd. So what's the degree of the first one? Odd. Either because you know it looks like a cubic, or because they are going opposite directions. How about the second one? Even. Third one? Even. Right? So going down doesn't mean even or odd. It only matters if they match. And then the last one are opposite, so it's odd. So lead coefficient, you got to get that one right first. Then you can look at even odd because it sort of depends on what the right end is doing. All right, so that's characteristics, the degree and the end behavior. And so a lot of times, as Cole already was looking at, the matching between those two things, you can figure out generally what's going on. Next, let's talk about zeros, roots, x-intercepts. And again, that's all the same thing. And this is sort of the last new stuff. We'll do some examples, but this is the last piece of information you need. if the graph bounces, quotes, because does the graph really bounce? Not like you're bouncing a ball, not that kind of bounce. If it bounces off the x-axis, then the root is a double root. A double root. So it counts twice if you're trying to count how many answers you have. If it bounces, it's a double root. We should be careful here. It could be a quadruple root or any even-powered root. 6x, 8x, 10x, I guess. ... Any even-powered root is going to bounce. So we just saw a picture of that a moment ago, but something like that. If it just touches and bounces, that's a double root. And with only that simple picture, I suppose it could be a quadruple root, but most of the time it's just going to be double. If it crosses, it's a single root. So that's one answer. That's sort of what we're used to. Yes, sir?
So number 5 on that same section, is that bounce? Or like, what is that?
Okay, so number 5 on that section.
Am I going too far?
Yeah, you're jumping up ahead to what's next. Like what kind of function looks like that?
Cubic.
A cubic. So if it wiggles through the, I don't know what else to say, wiggles, doesn't bounce, doesn't just cross straight through, but does a wiggle, then that's a triple root. And again, how you remember that is that looks like x cubed. And this double root looks like x squared. Like, don't look at the whole graph. If you just look close to the double root, it looks like a parabola. Away from the root, who knows what it's doing, but it looks like a parabola right there. Just like on this triple root, who knows what else this thing is doing. It might be doing crazy stuff. But if it wiggles while it goes through, that looks like an x cubed, so it's a triple root.
Is it only going to be triple, or is it going to be multiple?
An odd root.
Okay.
Or fifth, seventh, etc. Like we're not going to use fifth roots or anything, but in theory, just by looking at it, if it wiggles, you don't know for sure if it's 3, 5, 7 or 23. Let's see if I can speed up the notes to get ahead of Cole here. Imaginary roots I think we talked briefly about this yesterday. Imaginary roots do not cross the x-axis. Because if they cross the x-axis, there'd be a real number there and they wouldn't be imaginary anymore. Which makes them sort of tricky to see, because you're not, like, what am I looking at? If it's not crossing the x-axis, what am I looking for? Now, you can sort of learn to spot them. If there's something going on that doesn't cross the x-axis, so there's one real root that crosses the x-axis. If there's wiggles that don't cross the x-axis, like, again, I don't know where it is or how it is, because you don't see imaginary roots, but somewhere in there, something imaginary is going on when it wiggles without crossing the x-axis. Because that means you've got higher powers, but you don't have more solutions, so those solutions are imaginary. So wiggling without crossing, there's something imaginary going on. All right, lastly, and this is important, weird roots. Okay, we're using very technical language today. I'll define weird in a moment. Come in pairs. Weird roots come in pairs. Like, what in the world do you mean by that? Well, I'm going to say weird roots. There's two things that would make it weird. Imaginary, that's weird. That's no fun to work with. But also irrational roots. Irrational would be like square root of 7. Square roots that don't have nice square roots. You get irrational numbers. So we sort of stumbled into this yesterday when we were finding or using the quadratic formula, because we would get things like x equals 3 plus or minus 2i. That's a pair of solutions. That's two answers. And it came in pairs. So that's the imaginary one. Irrational ones, think to the quadratic formula. X equals negative b plus or minus the square root. Maybe it simplifies plus or minus, say, 2 square root 5. So they come in pairs. And more than that, it's not just any pairs. Do you remember the name? We've used it a couple of times. 3 plus 2i, 3 minus 2i. What are those called? Again, still you don't need to know the word, but it's helpful to talk about them. Starts with a C. Somebody said it. Conjugate. They come in conjugate pairs. And because they come in pairs, if we give you one of them, you sort of automatically know the other one. And that's what we use, or that's how we use that piece of information. All right, some examples. Let's find a third degree polynomial with zeros of -1, 2, and 3. Get my face out of the way. And a third degree polynomial with zeros of -1, 2, and 3. We did this a little bit yesterday, so think backwards. If -1 is the root, what was the factor? X plus 1. And if 2 was the root, then x minus 2. And if 3 was the root, x minus 3. Now there's two things I don't like about that answer. I want it multiplied out. So when multiplying factors, it's kind of like multiplying numbers. You can't really multiply 3 at once. Like even if you were doing 2 times 3 times 5, you do 2 times 3 is 6, and then you multiply it by 5 and you get 30. So you do it quick, but you still only can multiply 2 numbers at a time. Same thing here. So I need to pick 2 of these to FOIL and then distribute the other one after that. I don't know which one you want to do. It doesn't matter. I think I'm going to save x plus 1 for the end. So let's FOIL x minus 2, x minus 3. By the way, I'm assuming you can FOIL in one step. You don't need to write out FOIL. Write out all the terms and then collect the O and the I together. And then this one's not FOIL. This one we got to be a little bit more careful here. Let's distribute the x to everybody. So x cubed minus 5x squared plus 6x. And then we'll distribute the 1 to everybody. X squared minus 5x plus 6. And And then we look for like terms, x cubed minus 4x squared plus x plus 6. Yeah, there's still one thing I kind of don't like about that. And maybe it would have been better if I had clarified. Find a third degree polynomial equation. That's not an equation right now. What would make it an equation? Yeah, I just need f of x equals or y equals. So multiple choice, that's going to be obvious. Free response, you don't want to lose a point because of that. Let's find a fourth degree equation with zeros of 0, 2, and negative 3. Fourth degree equation with zeros of 0, 2, and negative 3. Okay, so already something doesn't quite line up here. Do you know what's not quite matching up? Right. Like a fourth degree equation means I'm supposed to have 4 answers. So what could I do to get a fourth answer without adding an extra 0? Make one of them a double root. It doesn't specify, so which one do you think would be the easiest to make a double root out of? I think the 0. You can make it out of any of them, but for multiplication purposes, let's make the 0 a double root. Because what? Maybe we don't know. The factor with 2 would be x minus 2. The factor to get negative 3 would be x plus 3. What factor would give us 0 as an answer? And you could back up and just say x minus 0. And then double root means you would square it. So x squared, x minus 2, x plus 3. So x squared plus x minus 6. Space, but I think I'll finish. X to the 4th plus x cubed minus 6x squared. And I'll just put a y on that one because I really am out of space. So we have a fourth degree equation. It only has 3 zeros because one of them was a double root. And I guess that means there's 3 answers to this question because you could have picked 2 to be the double root or 3 to be the double root, but your answer would have been more complicated. Still would have been x to the 4th, it just would have been uglier. Find a third degree polynomial with zeros of 0 and square root 3. Third degree polynomial with zeros of 0 and square root 3. It's a little bit like the last one in that third degree means there should be 3 zeros, and yet we only gave you 2 of them. So what's the other 0? Do you know what the other 0 is? Yeah, what's the other 0? What? X equals negative square root of 3.
We Yeah, like I was saying.
Oh, you're ready to put them in factored form. So x, and then x minus root 3, and x plus root 3. But let's back up a second. This is the conjugate pair thing. If you get one weird answer, you got to get the other weird answer. They come in pairs. But it's kind of nice that they come in pairs because when you multiply conjugates, the middle terms go away. X squared. I guess we could show it, although I hope some of you are beyond showing the O and the I of conjugate multiplication because you know it's just going to go away. And then we still have that x out front. So x cubed minus 3x. And then to make it look official, I can put an f of x on there. But the main point of that problem was if you get a weird answer, you automatically have two weird answers. But when you multiply them together, like the weirdness goes away. Like two weirds make a not so weird. Cole?
So that one's basically like number 13.
Is it exactly like number 13?
Except it says the 0 in the square root of 3. It already puts it.
Yeah, I gave it to you. So I need to do a different example next period. So note to self. You don't do this. I'll do this. I'll make it square root of 2 next time just to change up the example. But yeah, this is like number 13 on the...
The first one we did was like number 10.
Like it, but not exactly like it? It may have been exactly like it. Thank you. We'll switch up my my notes here. So let's make it 1, -2, and -3. Switch it up a little bit. I don't know which came first, the notes or the worksheet, but they're matching too closely. Good news for you. Let's find a third degree. You don't change anything. Don't change anything. I'm changing things for future reference. A third degree polynomial with zeros. This time I'm going to peek ahead to make sure I don't do the same problem. Nope, I think I'm good here. With zeros of -3 and -2i. Well, again, we're short a 0, right? Third degree suggests 3 zeros. I've got 2 of them. What's my other one? Yes. The partner of -2i would be a positive 2i. So my factors would be x plus 3, x plus 2i, and x minus 2i. I kind of gave away the next question. It's your choice on which 2 of the factors you want to multiply together first. But I think there's a clear choice. Which 2 should we multiply it together first? Yeah, the conjugates, because that that should make things easier. X squared. It's our second conjugate, so by now I'm alert and I'm attention to the O and the I canceling each other out. So x squared minus 4i squared. Just a second. Which would be x squared plus 4 and x plus 3. So now I've got a FOIL problem. Cole?
You do want like number 12. Like, you do 2 solutions, but it's a 15.
Yeah, we'll do that one in a minute. Let's see, I got a FOIL, so x cubed plus 3x squared plus 4x plus 12. All right, one more. Then we'll do off the worksheet. You guys are jumping ahead. This one is going to be a multi-part deal. Kind of go the other way. We'll start with the equation, and we'll find all the stuff. But we'll walk you through the stuff we want you to find. We're not going to give you an equation and just say, find the stuff. You wouldn't know what we're talking about. Let's find the zeros first. So we'll set this thing equal to 0. Whoops, that should be x squared. Otherwise, this is going to be a weird problem. Negative x to the 4th plus 16x squared. All right, how do you want to solve that thing? What can we factor out first? I would do a negative x squared. So that would leave x squared minus 16. That's convenient. It's nice when they rig the problem to work out for you. Oops, find the zeros. I almost made the mistake that I've warned you about. I finished factoring, but I haven't found the zeros just yet. So x equals negative 4 and x equals positive 4. Those are the easy ones. What about this x squared? What does that lead to? A 0. And the fact that it's squared, what's that mean? It's a double root or a bounce. And so I want to make a note of that because I'm going to need that in a moment. It doesn't matter here yet, but in a moment I'm going to need the fact that it's a double root. All right, in behavior. All right, the right end. What's the right end doing? Down or up? And how do you know? Why down? Down because it's a negative lead coefficient. Down because we're looking at the lead coefficient. Now I also want us to be able to write these in behaviors with some symbols that become helpful in calculus. As x goes to infinity, that would be the right end. If we're going down, then what's y headed toward? Do you know? Negative infinity. Okay, good. So it's a little bit new, but I think it makes sense. So the right end means as x goes to infinity, if we're headed down, that means y goes to negative infinity. So that's a fancy way to write everything that we just wrote. How about the left end? Down or up? Why down? I agree that it's down. Yeah, even means same. And so the fancy way to write that would be as x goes to, what's the left end? Out that way. Negative infinity. Y goes to, we're going down, so also negative infinity. And then lastly, we'll have you sketch it using all the information we've got. So let's see, I've got a 0 at 0. In fact, that's a double root. 0 at 4, and at negative 4. All right, we said the right end is going down, or as x goes to infinity, y goes to negative infinity. So the right end is going down. the left end is also going down. So as we come off the left end here, we're also going down. In the middle, we kind of have to just piece it together. -4 and 4 are single roots, so nothing crazy is happening there. Those just cross. Okay, no wiggles, no bounces, just a cross. At 0, there's a double root, so there needs to be a bounce there. Do you think it's going to be is it going to be like a downward bounce or an upward bounce? What would fit with the rest of the problem? An upward bounce. If it's a downward bounce, we'd have to have another root in there to make that work. So upward bounce. And again, that's just a rough sketch because who knows exactly how high it goes or how sharp the turns are. Like, we don't need to know that. But we do have a pretty rough picture of what that graph looks like. All right, today's assignment is worksheet 4. So again, we're going in order, not going on the order of the calendar. And another reminder that due Friday is worksheet 1 through 3. Hopefully they're done by now, but you've got time now to work on them if you would like. You can also work on worksheet 4 now. It's block day, so you got lots of time.